Hello, I'm Jason Lowdermilk with ChipScan. I'd like to talk about our experiences in applying zero trust principles to a full system architecture through a process we call the hardware up method. The primary security goal of this process is to start with a software-based system and move the functionality out of the application layer and into the hardware layer. The reason we want to do this is to drastically reduce the overall size of the attack surface. Full systems are typically built within layers, with the application layer on top. This can be relatively small, but relies on application frameworks and libraries that can be considerably larger. Below that is the operating system, which can have millions or tens of millions of lines of code. And there are further layers of abstraction below that, as well as all of the hardware components. We like to think of security as a full system property that includes all of the software as well as all of the hardware. It is very difficult to apply zero trust principles to a full system like this, since it requires securing every software and hardware component in the system, including all of the interfaces between them. When people talk about zero trust, they are usually referring to securing network interfaces rather than the full system. Small systems tend to be more secure than large systems in general, since they are more amenable to analysis, which makes them more trustworthy. The main question we are investigating is to what extent can we reduce the attack surface in a realistic setting. The resulting system needs to be functional, but also needs to be usable and maintainable. How will this process affect the system performance, and how does the productivity compare to a normal software development flow? The answer to these questions depends on the context. For this project, we chose to study a part of the satellite ecosystem. What I'll do first is give a background on this part of the ecosystem. As you'll see, the functions that it carries out are deceptively easy to describe, but the implementation tends to be very complicated. Then I'll show our new architecture that substantially reduces the attack surface. I'll talk about the steps we use to achieve this, which includes using high-level synthesis to migrate software into an FPGA, some significant memory safety improvements, and the techniques we use to make sure that the hardware being used can be trusted. Finally, I'll conclude with some results and reflections on future research. The type of system we apply this process to is a satellite front-end processor, or FET. This is a part of the satellite ground segment that deals with the raw data coming off of the modem. The FET is responsible for cleaning up the data, decrypting it, and extracting data packets, which are then forwarded to the command and control, or C2 system. The data from the modem consists of raw, non-byte-aligned data, so frame synchronization is done first, followed by de-randomization. The data is randomized by the spacecraft to introduce bit transitions, which make it easier for the receiver and the modem to maintain lock. The arriving data will likely have bit corruptions, which are corrected through a type of forward error correction, usually a Reed-Solomon code. After the integrity is validated, the data is decrypted and packets are extracted, which are then forwarded to the C2 system. FETs are typically software-based and are composed of multiple computer systems. There's usually a black side FET that works on the encrypted or ciphertext data, and a red side FET that works on the decrypted or plaintext data. In between these are cross-domain solutions such as cryptos and data guards. FETs can be quite large in total, since they are usually composed of multiple strings of equipment and include additional equipment for the infrastructure. So they can have a large footprint in the control center consisting of multiple rows of rack-mounted servers. Next, I would like to walk through the architecture of our system at a high level. We chose to implement our design using an FPGA, which can be deployed in both a local or on-premises version and a cloud version. The component architecture is data flow based. The system is implemented as a network of feed-forward data flow modules, and data moves through the system much like a conveyor belt. First is received by the physical layer, and then a UDP module, and then a preprocessor module that extracts the contents of the UDP packet. Then frame synchronization is performed, followed by de-randomization, and then it goes to a parallel Reed-Solomon decoder. Then a CRC module, which is used for data integrity validation. The data then reaches the decryption unit, which is implemented in stages. The first stage extracts the plain text portion of the frame and uses it to build the initialization vector that's required for CFB mode. The encrypted portion of the frame is forwarded to the decryption units, and the newly decrypted data is then reunited with the previously extracted plaintext data. This complete frame is then forwarded to a packet demultiplexer, which extracts the data packets and passes them back up through a TCP/IP stack to the physical layer and then onto the C2 system. cloud version is hosted on the Amazon F1 environment. In this configuration, it's very similar to the on-premises version, except it does maintain a small layer of software, which is used to receive UDP datagrams. In this configuration, the host application is necessary because we aren't able to completely shut down the software environment, otherwise the instance would be reclaimed. The software receives UDP datagrams, pushes them through a FIFO through the Amazon shell, which is a piece of custom logic that gets put into the FPGA when it's deployed in the F1 environment. From there, the processing chain is the exact same as the on-premises version. It comes out the other side, goes back through the Amazon shell into software, and from there it gets forwarded to the C2 system. We have a similar layout that supports the commanding pathway. In the case of commanding, the data flows in the uplink direction, so the commands originate at the C2 system. They're received by the networking layer. They pass through CFP encryption, then randomization, and BCH encoding. In the case of commanding, the forward error correction is typically done with BCH codes rather than Reed-Solomon codes. It then passes through a CLTU generation stage, which prepends and appends specific byte patterns, which turn the message into a command link transmission unit. This is then fed through the networking layers and then onto the modem for transmission. The cloud version is very similar to the downlink version, where the network interfaces are managed by a small F1 host application. So with this architecture, we can deploy a full-featured FEP in a very small form factor, both as a local instance or as a cloud-based instance. Next, I'd like to talk about some key technical steps to increase trust, starting with migrating software to the FPGA using high-level synthesis. High-level synthesis is the process of using a high-level language to describe hardware. We use high-level synthesis in two different ways. The first is to convert legacy code into Verilog, which can then be synthesized into logic for the FPGA. In some cases, the algorithms that you want to migrate are already available in a language that can be converted directly into Verilog, such as C or C++. For this, we use Vitis HLS, which is part of the Xilinx Vivado suite. The second way that we use high-level synthesis is to implement new functionality using a high-level language that compiles directly into Verilog. For this, we use Clash, which is a type of Haskell that's suited for hardware development. By using high-level synthesis in these ways, we're able to maintain many of the benefits of using a software development flow, such as productivity. Next, I want to walk through the steps that we followed to migrate functionality from legacy C code into the FPGA. In this case, we were interested in using an open-source Reed-Solomon decoder of a specific type that is required by the FEP. The legacy code was written with the assumption that the frame data to be decoded is stored in memory, with the top-level function receiving pointers into that memory. The FPGA implementation uses memory in a different way, and we need the function to work in a streaming manner instead. So the first step was to refactor the C language code in order to buffer memory internally and operate in a byte streaming manner. Each call provides a single byte to buffer and simultaneously returns a single byte from the same buffer position containing decoded data from the previous frame. Once all the bytes making up the code block have been received, the function will initiate the decoding process. This effectively makes the C code work in a byte streaming manner. Next, we use Vitis to convert this C code into Verilog, effectively making a byte streaming Verilog module. Then, we bookended this component with serializer-deserializer components implemented in Clash, which basically convert from serial to parallel and vice versa. This effectively turns the module into a bit streaming mode, which makes it compatible with the rest of the architecture. The final step was to deploy multiple instances of this bit streaming component with a round-robin scheduler, which makes it work as a parallel decoder. We deployed 64 instances of the decoder in order to maintain real-time data flow at the maximum bit rate, based on the maximum number of clock cycles required to decode and correct a single code block. Next, I want to talk about memory safety improvements. Studies have shown that the majority of security exploits are related to memory safety. This is a major benefit of the hardware-up approach. Since our hardware-based architecture offers complete memory safety, it does not have things like stack frames to corrupt or instruction pointers to overwrite. In some cases, like we saw with the Reed-Solomon decoder, legacy code may require some refactoring to adapt dynamic memory usage in the static memory. As was the case with the Reed-Solomon decoder, this can be a very straightforward process. Next, I will talk about avoiding hardware backdoors. The traditional concern for hardware backdoors is the insider threat case, where the developer is the bad actor and is intentionally inserting backdoors into hardware designs. But in some cases, the developer is instead the victim and may be targeted by hackers. Specifically, the EDA tools they use can become compromised so that they insert backdoors without the developer's knowledge. Two places in the development flow where this can happen are in the conversion step from high-level code into synthesizable Verilog, and also in the synthesis step, which converts the Verilog code into a netlist. Our solution is to use a scanning tool called SB, which is one of our tools that we make commercially available, which is able to scan Verilog and synthesize netlists to find stealthy hardware backdoors. This tool is used as a constant part of our development flow to ensure that no backdoors are being inserted by the EDA tools being used. It's also possible for hardware to have other types of trust issues. In particular, general-purpose processors can have unfixable flaws such as Spectre, and we believe there's a high likelihood that processors contain additional vulnerabilities which have not yet been discovered. Our solution is to avoid the use of general-purpose processors. Modern FPGAs generally bundle custom logic devices, such as processors and memory controllers, with their products. But because we are not able to actively scan or inspect these devices, we avoid them and only use the reconfigurable portion of the FPGA. This also reduces the risk of a targeted backdoor being inserted by the foundry that makes the FPGA, since the attacker would have no way of knowing how the hardware components would ultimately be placed in the reconfigurable logic. Now for some results and reflections. In terms of trust benefits, our approach significantly reduces the overall attack surface. We conservatively estimate by a factor of 100 for the cloud version, and this approach leads to complete memory safety. In terms of productivity, the use of high-level synthesis provides a hardware development flow that is very similar to a modern software flow. It allows for techniques like fuzz testing, which are not generally used in hardware flows, and it allows for a high level of productivity. We were able to implement a full-featured FEP in 18 person months. In terms of performance, our cloud-based system is able to sustain a bit rate of 125 megabits per second, which compares favorably with software FEPs, which typically operate in the 20 to 30 megabits per second range. And because of our limited use of memory and buffering, the system has very low latency. Now some reflections on the overall process. There have been recent improvements in hardware tools, such as the ability to convert legacy code into Verilog. This is a capability that's been around for a long time, but traditionally has not been considered reliable. And there have been recent developments in high-level languages that compile into Verilog, such as Clash and Chisel. This makes it possible to apply software fuzz testing techniques to hardware designs, and tools exist now that can reliably find hardware backdoors. Many of these tasks are not possible with full-fledged software flows. As for our experiences using cloud-based FPGAs, it is a nice feature to be able to deploy an FPGA in the cloud, but it does have room for improvement. In particular, it would be nice to have the ability to completely shut down the software stack without having the instance reclaimed, and deploying custom logic into the FPGA currently requires the use of custom logic devices such as the Amazon shell, which are proprietary in nature and cannot be actively scanned or inspected. Security without trust is not possible, and a long-standing goal of securing systems is to reduce the amount of trust that is required. The hardware-up approach offers an alternative to formal verification and homomorphic encryption techniques for hardware assurance, and we've shown promising results, but this is only one result, and we need more results to better understand the generality of the approach. We believe this method could be easily applied to other types of mission-critical systems. Thank you for listening, and let us know what questions you have.